So hello everyone, welcome to this first webinar of the AFRICAI network. It's a great pleasure to have you all here. I just want to present a few slides just to tell you why is it that we want to do this, this network and what are our objectives and what we'd like to get out of it. So first of all, some introductions. I will start with the members of AFRICAI that have already signed up, to say that the 28% are academics that work at universities, 22% are master students, 20% are PhD students, and then we have bachelor students, postdocs, some clinicians, and some working in industry. So we have a nice diversity of profiles. So I hope this will be a great forum for collaborations. These are the countries we have so far that have signed up. Almost half of African countries are represented. And I hope with time we will be able to extend the network. And we have also some African researchers based outside Africa that signed up as well. And also we have a third of the members who signed up who are female and two-thirds who are male, which is, I think, a good ratio to start with. And I hope with time we will be able to improve this. So these were the members that have signed up. In terms of the organizers, I would like to say that this is very much a team effort of different members of the community based in Africa, but also outside Africa. So today you will meet Tinashe and Celia, who will present something in a few minutes. And just to say a big thank you to Nusair, who created the website and organized all the registrations. So he's not here, I don't know if he's here today. And then over time, you will meet all the other members. Just to tell you, for example, that Anis, who is now a postdoc at Harvard, will organize the next webinar, which I think will take place on the 22nd or 25th of June. And how do we know each other? So we know each other through the MICAI Society. So what is the MICAI Society? It's the Medical Image Computing and Computer Assisted Intervention International Society, which exists since '98 and organizes all sorts of activities in the field. So annual meetings and conferences, but also publications, workshops, tutorials, challenges, which are kind of competitions to compare and benchmark algorithm, and also mentorships. So these are examples of papers that have been published at MICAI. The first one is a very famous paper. It's the UNET. So if you work or if you will work on deep learning for medical imaging, at some point you will most probably use UNET. So this was a paper that was presented at MICAI, and these are two papers that were presented by researchers based in Africa, and some of which you will hear today. And something of particular interest are the challenges which are organized at MICAI. So these are competitions based on open data, which allow people to participate and try their algorithm. So if you go to this website, you will find that there are already a lot of data that you can download and use, so you can play with your algorithm and see how they perform. There are also workshops that are organized at this MICAI conference. So last year there was one called FAIR MICAI, which is affordable healthcare and AI for resource diverse global health. And there will be another version this year at MICAI 2022. 2021 took place in Strasbourg. 2022 will take place in Singapore. And in the history of MICAI, the first one was in '98 in Boston, and then it took place 10 times across the American continent, a number of times in Asia and Australia as well, another 10 times in Europe, and actually yet it was never organized in Africa. So that's how we actually met. We had the objective to submit a bid so we can propose the organization of the MICAI conference in Africa in 2024. This is the committee. There are probably other people that will join the committee, and some of which decided to create the AFRICAI network. So the bid was accepted, which means the first MICAI to take place in Africa will take place in Marrakesh, Morocco in 2024, and we hope we will see you all there. To say that in creating the AFRICAI network, we were inspired a lot, but already existing works across the African continent to promote more work in AI and in data science, in particular deep learning in DABA and Data Science Africa, who are doing an amazing work, and I'm sure you've already heard of them. To say that we thought to create a network focused on biomedical imaging because it's such an important area for AI. There's a lot of research in the field that is increasing every year. So 5 years ago, there was less than 1,000 papers indexed in PubMed, and last year it was almost 6 times that. So there are often new works that are disseminated in the media and describe all sorts of solutions to improve medical imaging and radiology, yeah? For example, for breast cancer or coronavirus or for skin cancer. This is a website that shows the list of FDI-cleared AI tools in medical imaging. So it's a very interesting website. At the moment, there are more than 150 tools. It gives you an idea of what already exists, what is being commercialized, and what can be used actually in the real world. So among the AI tools that exist in medical imaging, it's worth mentioning those that do quantification, because what they do is relatively simple and sometimes very important. They allow to perform automatic quantifications of the images. So this is, for example, a cardiac MRI image. And instead of having a cardiologist or radiologist manually delineate this image or a set of images, which takes about 45 minutes. With deep learning, it takes now 1 second to do. So it's a lot of resources that are saved and can be used for other things in clinical practice. This is a figure that shows the number of radiologists across the world. And as you can see, there are places that have a lot more radiologists than other places. And in areas where there are few radiologists, such as across many African countries, artificial intelligence is expected to play an important role, because there is a gap that it will be able to bridge, and by providing a service such as automated diagnosis based on imaging. And this could be used, for example, to improve care or improve diagnosis. This is an example of an AI tool that was developed actually by Google, that received some attention in the media because it showed that it could detect tumors that the radiologists couldn't. So this is an example of 6 radiologists that were not able to see these tumors here, but the AI was able to identify these. And this is because the tissue here is very complex, and this is where AI has also a lot of potential. This is another example of a study that compared 12 different artificial intelligence solutions for the detection of tuberculosis, or something that is relevant for Africa. And it's shown that in 3 cases, it performed better than radiologists with intermediate experience. To say that we looked at the works in AI in some key journals, Medical Image Analysis, Radiology Artificial Intelligence, and Journal of Medical Imaging. We looked at every paper last year in 2021, and we saw that most came from only 20 countries, over 95%, and many countries still do not are still not represented in the scientific literature. So there is a gap, and that's why we think this AFRICAI network can have a major role because there is a clinical demand, including in Africa, to deliver diagnosis and other clinical tasks using medical imaging and AI. And at the same time, there is a lot of potential, as I mentioned previously. The deep learning in DAB and data science Africa have shown that there is a lot of human potential in the artificial intelligence field. So the objective of the AFRICAI network will be first to promote more research and innovation across Africa in the field of AI for biomedical imaging, to enhance education, training, and mentorship, to promote collaborations, in particular between engineers and clinicians. We think this is very important.
No, that's what you used to select whether. So, study selection.
Clinical practice,
It's supposed
seminar,
to be bad.
public health.
It's supposed to be bad.
Practice me at 12 credit hours.
It's supposed to be bad.
Okay, I had to mute someone. Okay, so sorry, I have to go back to the previous slide. Here we are. So enhance education, training, and mentorship, promote collaboration between engineers and clinicians, and develop a culture of responsible sharing African data. This is important because without data, we cannot do much AI, and we need data, imaging data that come from Africa that correspond to the local populations, and then develop real-world solutions for Africa by Africans themselves. So the way to do this, first we will organize regular webinars, and we already started. Hopefully we can do it monthly. Sometimes we'll do it every 2 months, depending on the demand. So we will ask you to tell us how often do you want it and what sort of webinars you would like to have. We'll organize summer schools. So the first one we'll have in August 2022, and we will have one. So this one will be online, but we will have one in 2023, probably hybrid. Partly presential. It will be in Marrakesh, and also online, and hopefully we will be able to invite a lot of you to be part of this summer school. We will also want to add a mentorship program, in particular for students, networking events, for example, with companies, but also with hospitals. Hopefully we will be able to find sponsors and have sponsorship, in particular for traveling, so the students and postdoc and other researchers will be able to attend these conferences, like the summer school next year or the MICAI 2024 conference in Marrakesh. And then we would like to organize datathons, which will be events where we will discuss the collection of new data and the analysis of the new data, and hopefully the data will be from Africa. This is an example actually of a personal experience with my student Carla, who will present later, where we did some work based on data from Europe, but also from 5 different countries across Africa. And it was really a very nice experience and quite a positive experience, where we contacted different places across Africa, and there was a positive response and a very nice collaboration, where we learned from that collaboration by understanding the clinical needs and the sort of solution that need to be implemented. And I think it was a very nice experience, and therefore I would also recommend that this exercise is repeated by sort of talking to hospitals and clinicians and having this conversation as to how to exploit the available data nowadays in Africa. Okay, so our target would be to have a large network of researchers, students, clinicians, and other stakeholders within the AFRICAI network. We would like to increase the number of papers in journals, but also in conferences such as MICAI. We would like to increase the number of available data sets from Africa, so we can train and evaluate new AI solutions. Obviously, the number of projects for students, so they can train and become future experts in the field. Number of mentorships, new collaborations within Africa and internationally. And I hope we can find sponsors so we can increase also the number of attendees in conferences. So if you want to participate through the AFRICAI network, please contact us. You could be part of the organization team. You could present your work at one of the webinars, for example, the next one, 22 of June, or the next one in July, or later on. We could discuss research project with the organization team or with somebody else in the AI for biomedical imaging community in Africa or beyond. You could propose an activity or event, and you could also tell us about biomedical imaging in AI in Africa. And this is very, very important because we would like to understand what are the needs, what are the barriers, and what are the opportunities. Finally, of course, you could make any type of suggestion on how to improve this network. Okay, so thank you for your attention. Just to thank again those who helped us create this network. So we are really early days, and we hope this will lead to interesting results and collaborations. And so we look forward to your participation. And as I said, if you have any suggestions or any way to contribute, any presentation that you would like to add to the programs, let us know. Okay, so I don't know if there is at this stage any question or any comment or suggestion regarding the network itself. You could write it down also on the chat if you prefer, or you could open your microphone and ask the question. If not, I propose we move to the first presentation. So we were going to have 3 presentations, but we will have only 2 today. We will have one a joint presentation by Tinashe and Celia on machine learning for medical imaging across the continent. They will give you in particular examples from South Africa, where Tinashe is based, and also from Eastern Africa, where Celia is based. And then later on, Carla will describe some work that she did in collaboration with 5 centers in Africa on fetal ultrasound. So Tinashe, that's your turn now.
Thanks, Karim. Are my slides showing? Good. So good afternoon, everyone. My name is Tinashe Mutshangwa. I'm an associate professor in biomedical engineering at the University of Cape Town in South Africa. And my co-presenter is Dr. Celia Sintas, who is a research scientist for IBM Research in Nairobi, Kenya. We'll be talking about machine learning for medical imaging on the African continent. But just to start off, as a disclaimer, Africa is a big continent with a lot of diversity in healthcare, in terms of context, resources, policy, etc. So please accept that our presentation is biased towards our own contexts, which are South Africa for me and East Africa for Celia. And just to reiterate what Karim said, diagnostic imaging is a key component in modern healthcare. It plays a vital role in the diagnosis and prognostication of disease, as well as in monitoring response to treatment. And the number of radiological examinations performed has increased greatly over the past few years, largely due to technological advances in imaging, increased availability of imaging facilities, and of course, the rising demand by both patients and healthcare workers. So what some of you may not know is that Africa has made an immense contribution to the technological advancements of medical imaging. Here is a list of some of the notable innovations and also some research resources that have come online in Africa recently. So the CAT scan, or the computed axial tomographic scan, was theoretically conceived of by a South African physicist, Alan Cormack, who shared the Nobel Prize in Physiology with Godfrey Hounsfield for its invention in 1979. Also, the first full-body X-ray scanner, which I'm showing here, was developed in 2002 in South Africa, which was a collaboration between the De Beers Diamond Company and researchers at the University of Cape Town. The Cape University's Body Imaging Center was came about in 2007, and in 2015 they acquired the first research-dedicated MRI facility in Africa. Also recently, the AFRICAI system, which is shown here, which incorporates a full-field mammography and automated breast ultrasound, was tested in 2014 and CE marked in 2017. So there's a lot of contributions that we can that can be accounted for on the African continent. But while Africa has contributed to radiological imaging innovation, the benefit from this important technology is not always accrued to its inhabitants. Basically, huge disparities exist in the availability of radiological services between the developing and the developed world. An example is the availability of CT units per 1 million people. So Molura et al. In 2013 noted that across Africa, on average, there was 1 CT unit per 1 million people, which you can compare to a country in the global north, such as Denmark, which has 24 CT units. And of course, this availability has changed a little bit, but not enough. As you can see, in a study from 2001 by Gature et al., the number of CT units shown here in red registered in 6 sub-Saharan countries are not much more, there hasn't been much more of an improvement. Furthermore, within these countries, there exist differences between availability in the private and the public sector. And this cuts across all the imaging devices. But here I'm illustrating in yellow the differences between sectors for X-ray. And what you can see is that although the private sector only serves a small fraction of the population in most African countries, there's a disproportionate availability towards of the limited resources in this sector rather than in the public sector. Finally, it's also worth noting that the World Health Organization recommends that 20 X-ray or ultrasound units per 1 million people should be able to serve 90% of a country's population. But we see here in orange that at least 3 of the countries in 2021 were not meeting this recommended amount of devices, at least for X-ray. So what can be done to reduce these disparities? Well, there are a lot of things that can be done from a policy perspective, etc. But from a technology perspective, which I guess a lot of you are interested in, the following 4 have been suggested as ways to improve access to medical imaging in low to medium income countries. These are teleradiology, portable battery powered ultrasound systems, non-radiological imaging, particularly of the type that leverages optical imaging. And this is actually quite fortuitous because in South Africa, so in Africa, we have a large penetration of the smartphone. And last but not least is the use of artificial intelligence, which is the most promising technology of our time. So I'll briefly speak about the examples of the first 3, and then we can spend the rest of this presentation focusing on AI in healthcare generally, and then in medical imaging specifically. So teleradiology is electronic capture, transmission, storage, and retrieval and display of radiological patient images. And it allows for simultaneous sharing of images with other clinicians in other locations. It obviates the needs for losing images and facilitates more interpretation, so remote interpretation and consultation. It's promising because it allows for the sharing of resources and promotes cross-sectorial collaboration. And it has been particularly useful during the COVID pandemic. An example of an architecture of such a system is the one reported by Morgi and colleagues in Kenya, which I'm showing here, which is a system that improved the timeliness for radiologists to access images from remote sites. It enabled the radiologists to manage their time more effectively and alleviated the need for them to shuttle between different facilities allowing for efficient monitoring and turnaround times for reporting on images. Ultrasound equipment has become compact, portable, of much higher quality, and also the price or the cost is reducing with time. And this has led to the emergence of point-of-care ultrasound, or POCUS, as you might find in the literature sometimes. Now, these devices can be brought to the patient and performed, and the imaging can be performed by a treating clinician in real time, which allows the findings to be directly correlated with the patient's signs and symptoms. Nowadays, we have such devices also leveraging commercial smartphones or tablets for visualization, and through Wi-Fi and cellular communication, you can send the images to the cloud for remote processing, for consultation, etc. So here I'm showing an example of a portable ultrasound being used at Kiboka Hospital, which is a remote understaffed hospital with no imaging facilities and only one local physician on call, and it's in Uganda. Now, the resident physician, in order to use the system, underwent 5 days training and was able to consult with experienced radiologists and cardiologists abroad who were able to visualize both the ultrasound scan and the patient with the use of cellular phones and commercially available video chat software. The augmentation of the physical examination using such a pocket-sized ultrasound machine in rural Uganda has led to significant clinical findings in 70% of cases and to change in case management in 87% of the cases. In 30% of the scanned patients, life-threatening findings were found. So this is quite an interesting sort of benefit from using this technology. And as I said before, the combination of increased use of mobile devices in Africa and increased access to the internet generally, and lack of access to healthcare on the continent provides an opportunity for the implementation of effective mobile health or mHealth tools. So non-radiological imaging, particularly using smartphones, is increasing globally, but it has a lot of potential in Africa because of smartphone penetration. For example, here we have a mobile phone-based, there have been reports of mobile phone-based microscopy of sputum smears for diagnosis of active TB. And as reported, and as I'm showing here, this is some work done in my research group on developing a smartphone-based image evaluation for latent TB infection. Now, this tool makes use of a mobile application developed on the Android platform to capture images of an induration, which is basically the bump that forms after a patient is injected with the tuberculin reagent. And the system enables capture of images by the person being screened for latent tuberculosis infection or a community healthcare worker, and reduces the need for the patient to return to a healthcare facility for the induration reading, which usually occurs 42 to 72 hours post-administration of the tuberculin. So now let's move on to the fourth of the areas that I referred to earlier, which is artificial intelligence. So AI is defined as the automation of activities associated with human thinking, such as decision-making, problem-solving, and learning. And of course, AI is fundamentally revolutionizing healthcare generally. And this includes radiology, where it's being incorporated into improving diagnostic image interpretation, prioritizing triage of work lists, quality control, safety monitoring, population health studies. There's a cornucopia of different ways that AI is being leveraged for healthcare. However, as I mentioned earlier, the complexity due to inadequate or absent radiology in resource-poor health institutions in Africa makes the path for us to adopt AI different from what you may find in a high-income nation. So an interesting article by Molura and colleagues advocates for considering the following three for whilst introducing AI to radiology in under-resourced countries. The first is clinical radiological education. Because there's a lack of infrastructure in Africa, which is also mirrored by a lack of expertise. So basically, simply inserting AI into workflows in a resource-poor health institution would not work without radiologists who are educated to interpret the AI outputs, to supervise the AI implementation, and to independently validate AI algorithms on local populations to address issues of generalizability. The second is infrastructure implementation, which is one of the more difficult ones, because for AI in radiology, the infrastructure includes medical imaging hardware, servers, information technology networking, fast internet service, picture archiving and communication systems or PACS, electronic medical records, etc. And so such systems need to be adequately developed before introducing AI on the continent. Last but not least is phased AI introduction. And this includes trying out different algorithms on a variety of platforms across different clinical contexts to assess the AI's accuracy and ease of use. It also includes raising public and patient awareness and piloting AI for patient cases and population health. Now, this is a nice playground that we can all play in. And to me, just respecting these three approaches represents an opportunity for co-creation across different sectors to leverage the AI revolution for improving medical imaging across the continent. So we can all contribute within these sort of three considerations. Nonetheless, as we progress in the medical imaging domain with AI, we need to address and be aware of challenges and concerns when co-creating solutions in the healthcare space. The solutions we develop need to be created through a collaborative approach, including all disciplines from biomedical, medicine, computer science, industry, policymakers, government, etc. We need to be able to address the difficulties in gathering, anonymizing, and annotating large clinical data sets. There's also a need to evaluate aspects of our solutions for issues of privacy, social, cultural context, and potential harm to marginalized communities, amongst others. And finally, during the co-creation step of AI research and development, we need to encourage equitable data sharing practices so that we don't have multiple geographies that have their data accessed and shared, but do not receive the same benefits as the data collectors and owners of the data infrastructures. Just to say that we are not alone in AFRICAI in trying to leverage AI for improving all aspects of life on the continent. Over the years, the African continent has created a great push forward in research, education, and in innovation in the field of machine learning, We have communities such as Deep Learning Indaba and their local chapters, Masakane, Data Science Africa, Africa Archive, H3A, Bionet, AARS, and more. And they've all contributed to a growing network and knowledge base of AI and its applications, and there now exists a very rich and I would say a diverse space for intra-continental collaboration. So we encourage you to look up all these communities which for many of them have representation in a lot of African countries. And finally, for those who are entrepreneurs amongst you, please note that there's a lot of innovation taking place on the continent and being commercialized. There's innovation in the space of device manufacture, as with Lodox, the full body X-ray company I mentioned earlier, and Cape Ray, that produces an integrated mammography device. There's innovation in the area of teleradiology, as with AccuRead Radiology in Nigeria. There is also Rolog, I think it's called Urology in Egypt, which also is in the space of teleradiology. In addition, of course, there's a growing amount of innovation in leveraging AI for image-based diagnosis, as with Algorithmi in Nigeria and Mino Health in Ghana. Now let's hear from Dr. Sintas, who will showcase some exciting use cases of AI in healthcare generally, and in imaging in particular in East Africa and South Africa.
Thank you, Tinashe. Let me share my screen. Can you see the full presentation more?
Yes. Yeah.
Excellent. Thank you, Tinashe. So now I would like to share some examples of both digital healthcare in Southern and Eastern Africa. We can find common challenges in the healthcare system and the policymaking space in these two regions, such as, for example, the burden of communicable diseases such as HIV, AIDS, and TB, and non-communicable like hypertension, cardiovascular diseases, diabetes, cancer, as well as injury and trauma. Furthermore, we see the disparities and the scarcity of healthcare providers as their geographical distribution, similarly to the equipment distribution that Tinashe mentioned a few minutes ago. And lastly, what we see is a need to define and better understand policies to improve MNCH outcomes. So given this set of challenges, of course, among many others, we are biased to our working teams. We see the improvement of quality of care and care continuity as key research topics. We also need to look on how to make sure that the solutions that we provide are trusted by the community. How can we promote data ownership by the users, physicians, and patients, as well as guarantee privacy settings, just as Tinashe mentioned in the challenges. Lastly, most of us will be working in a resource-constrained setting that we usually navigate in this health domain. So we need to be able to provide imaging solutions so health providers can access to enhance image information at a lower cost. So I wanted to show some examples of research done here at the Kenya Lab in cooperation with healthcare experts and policymakers around these topics. So for example, you can see Aisha's Walcott team assessing the perspective of the stakeholders around the management of hypertension in Kenyan private health sector. And they provide some recommendations on how to design and develop care continuity digital health solutions. On the other side, you can see Eric Odor team that analyzed the context for tech solutions for quality of care for hypertension patients with HIV. This gives you an example on management of comorbidities and patient quality. On the other side, we also have examples on how can we use machine learning techniques to provide information to policymakers. For example, in the space of family planning, we studied contraceptive discontinuation and uptake patterns in subpopulation levels. William Ogallo and Skylar team work with domain experts and policymakers for MNCH, studying ways to better understand neonatal mortality factors. And Seku also works with reinforcement learning and other methodologies for orchestration of set of interventions for malaria policymaking, but also for other disease modeling. These are some examples of studies around healthcare and machine learning using health population surveys or electronic health records, among many others, that could be a complement or overlap with also medical imaging solutions. So now we're going to show some examples from both Tinashe and myself's team, specifically related to machine learning and medical imaging. So one research project we can see is on the bottom left. Is a framework to be able to provide high quality 3D information from X-ray views. For this project, they use something called statistical shape models to adjust the 3D shape based on the information of the X-ray views. So this type of reconstruction can be used to aid in multiple clinical tasks such surgical planning, postoperative evaluation, and you are avoiding higher risk, higher costs, and relatively greater patient irradiation associated to the 3D modalities that we can see with computed tomography. The team also works on solutions to be able to pair multimodal imaging for a given patient. So they propose generative process for synthesizing valid, realistic, and pair CTs and MR image volumes. So all these type of or following these streamlines, this work was published also at MICAI 2020 that I think Karim showed on the first slides. On the other hand, I will talk a little bit while we are working on machine learning at dermatology here at the Nairobi lab. So as you can imagine, as in other medical fields, we can find disparities in the dermatology space. So for example, in African American populations, melanoma is often diagnosed at an advanced stage. And for ALM, the survival rates are 5% higher for Caucasian populations compared to the African Americans. In these pandemic COVID times, dermatologists started gathering a registry to be able to catalog the skin manifestations of the disease, but currently they reported a low amount of samples for African and Latin patients. So this paucity of images on skin manifestations for COVID for patients with darker skin tones is posing a problem because it makes the identification of COVID based on cutaneous manifestation more difficult for both professional dermatologists and the common public. Of course, these disparities are not new, and there is people in healthcare working on educational materials such as Mind the Gap from Malone Mukwende that teaches how to report clinical signs in darker skin tones. But we need to think that when we are deciding or co-creating these machine learning solutions in medical imaging, we want to ensure that these and of course all the disparities are not translated and amplified in our solutions. So I will show you 3 streams that we have inside machine learning and dermatology. They were done by a subgroup of these amazing researchers, masters, PhD students, dermatologists, from multiple institutions that you can see the references for each team. So first example was led by Tim and Newton from Carly Mellon, Rwanda. They spent a few months doing an internship at the Kenya lab, and this is the work that was presented at MICAI 2020. So they propose a framework to be able to automatically stratify the classification outcome by skin tone. Of course, for that, we need to be able to extract the pixels from non-disease area and be able to estimate the tone in an automatic way. After, we can do some stratification to get the metrics out of the model. So these had multiple, for the segmentation model, there was a mascara and CNN that was tuned for skin tones. Multiple data sets common in dermatology were used. And after we have the pixels from the non-disease area, we have a skin tone estimation to be able to bin these results. So in this work, they show that there is an underrepresentation of darker skin tones in common use dermatology datasets in machine learning challenges and benchmarks. So this is the type of information that we want to know when we share our models and we want to test it in real life. We need to make sure that the population matches to whatever we want to make the deploying. So after MICAI paper was out, we were approached by dermatologists at Stanford that they were wondering if we can apply a similar pipeline to evaluate educational materials that are used to train the professional dermatologists. So this would be an automatic way to quantify the representation of different skin tones and their condition manifestations shown to professionals during their education or training. Shocking or similarly to the machine learning example, the preliminary results that we ran across multiple dermatology textbooks used in medicine school for validation, they are showing an underrepresentation of darker skin tones equal to 10 or less % of the examples that are shown to professionals. So for this work, we are currently developing a pilot. So any professional can upload their slides, books, materials, papers, and they have a representation analysis of the show that they are working or they are sharing with their colleagues. The last branch of work is around how to make our machine learning models robust. So usually these models are assuming ideal conditions and that the tests or the clinical data that are taken comes from the same distribution of the training. However, this, of course, is not satisfied in most of the real world applications. So for example, in a clinical setting, we can have different hardware devices taking the pictures. We can have different setup context, lighting, diverse patient populations with different or unknown conditions. So this work was presented a few weeks ago on ISP, and basically was trying to show a method to be able to detect this type of out of distribution samples after the model is already trained and working out. The technique is called substance scanning, and the core developers, researchers are sitting here at the Nairobi lab. So we are pretty proud of that. And of course, since the beginning, not only we measure the basic metrics that we always see for accuracy or performance, but we also stratify by the skin tones. And of course, on the OOD detection, we also see an stability when we are looking to darker skin tones. And this could be going back to, or partially because the network that it was trained on was again data sets that don't contain samples for darker skin tones. So before closing, we wanted to share some exciting opportunities that were recently funded. The Computational Omics and Biomedical Informatics program will provide interdisciplinary training opportunities for PhD students and faculty members around fundamentals on data science, computational omics, imaging, machine learning for biomedical, and so on. So if you're interested in this, please do ask Tinashe on more information about this program. So thank you again for your time. So in this presentation, we wanted to share an introduction to the current state of the field in some parts of the continent and examples of research that is being developed here and across at least Southern and East Africa. Now we really want to hear your thoughts on the topic. What exciting projects are you working in your country? What challenges are you facing on the space? If you are interested in presenting your work on the next seminar, please reach out. You can contact us via the link. And then if you scan the QR code, there is a link for a live poll when you can answer these questions, and we will gather together the information. Thank you very much. Back to you, Karim.
Okay, thank you, Celia. Just wondering if anybody has a question or a comment. If not, we'll go to the last presentation of the day, which is by Carla.
Yes.
On the application of deep learning and transfer learning for fetal ultrasound across 5 African countries. Go ahead,
I'll
Carla.
share my screen.
Yes.
Can you see it?
Yes.
Okay. And subtitles should work?
Let's see. Yes.
Yeah, I think so. Okay.
All right, cool.
Let's start. Wait. So thank you so much for joining us. I'm Carla I'm a student from University of Barcelona, and I'm working at BCN AIM lab. I'll be presenting the work I've been doing the last months, and I prepared this presentation so that everyone, independently of the background regarding AI, can understand it and can follow it. So I really hope you learn new things and that you enjoy it. We entitled this work as Generalizability of Deep Learning Models in Low Resource Imaging Settings, and it is a fetal ultrasound study in 5 different African countries. Okay, let's start. So first I will talk about the technical problem, which is how to deal with AI in data-scarce environments. And then we'll see this technical problem in a specific clinical application, which is fetal ultrasound in Africa. Later, I will explain you the methods, which were convolutional neural networks and transfer learning. If you don't know how they work, I will give you a general idea so that you can understand. And pay attention on transfer learning because it's a technique that helped us to deal with the technical problem, and it was really important in this work. Then I will show you the results we got in 2 European countries and also in 5 African countries. And finally, some takeaway messages. So as you know, the world's most valuable resource nowadays is data, and it's used to build artificial intelligence to train AI models. AI models are really data dependent, so they need a lot of data to work and perform well. And most of them have been implemented and applied in high-income countries. This means that the data sets right now were acquired most of them were acquired in high resource settings. This means that the quality of this data is high. You have a lot of data available in these data sets, and the data acquisition is similar. And this is a problem because, for instance, in the healthcare sector, this could increase inequalities in global health because these AI models could have been implemented just to be applied in high-income countries and not in other contexts in low-resource settings. So here we identified the need to build inclusive AI solutions that would also consider these data sets in low-resource settings. Okay, sorry for this. Okay, so a solution to this problem could be to train an AI model using the data set in low resource settings. But we know that this is not gonna work because in a data set in low resource settings, you don't have a lot of data. And as I said, this model needs a lot of data. So this model will not perform well. Another possibility would be to train an AI model with a data set that was acquired in high resource settings. So you have lots of data available. This is gonna work. And then just apply this model directly in a new context, in a new center, in a new data set in low resource settings. But again, this is not gonna work because AI can't perform well on unseen data. So in this case, the model will perform really good in this data set in high resource settings, but then in low resource settings, the performance will be bad. This is why here transfer learning can be useful because can adapt and realign the model in this new data set in low resource settings. The clinical application, we will see this technical problem in this specific clinical application, which is fetal ultrasound. As you know, an ultrasound examination is essential for pregnancy diagnosis and is used to check whether the baby is growing in healthy conditions, whether the pregnancy is in risk or not. And it's important to avoid neonatal deaths. The protocol that the doctor follows during the ultrasound examination is called fetal biometry quantification. It's quite easy to understand, but it's difficult to do it. So the first step the doctor does is identify the common or the most important fetal planes. which are the head of the baby, the abdomen, and the femur. Then the doctor is able to measure these distances that we see in different colors, which are called fetal biometries. And with these measures, with these values, with these fetal biometries, the doctor is able to make the diagnosis. The main issue is that, well, you need trained clinicians to do this protocol, and it's also really time consuming. This is why in countries with the shortage of trained clinicians and with less resources, as the neonatal death rates are really high, as we can see here in this worldwide map. So in these countries, the opportunity to identify and manage risks during pregnancy is limited. This is why here we thought that maybe AI could be useful, could be a solution to automate the process. So the whole ultrasound examination I explained before, and support the clinical workforce for the diagnosis. So my question was, has this been done before? And I checked it in the literature, and it was done before, but again, these models were just implemented and built in high-income countries. In this case, I will show you one example in UK. They built this AI model to automate the ultrasound examination. And I will explain you just a general idea for you to understand how it works. It's based on 3 different AI models. The first model is a classifier, so it takes the images during the ultrasound examination and classifies them automatically in these 3 fetal planes, which are the head, the abdomen, and the femur. Then you have a second model that would take these images already classified and would automatically segment the anatomical structures. Now, in this case, the head, the abdomen, and the femur. And with these segmentations, you have a third model that would estimate the fetal biometries that I explained before. So the doctor here just needs to check the values of the fetal biometries and make the diagnosis. The whole process is automated, so the ultrasound examination becomes easy and fast to do, thanks to AI. In this work, we just focused on the first model, which is the fetal plane classifier, to make it easier. So this was our start. Okay, for those who do not know how a classifier works, I will give you now an overview. In this case, the classifier used a deep learning model. Deep learning is a type of AI technique that is quite used right now for lots of applications, and it works really well. It just needs data to learn. These deep learning models, what they do is they process an image. They take the pixels of an image, the intensity values of this image, and by using this information and also the position of each of these pixels in the image, the model is able to extract this information and make the final decision, which is the classification. In this case, the classification is head, femur, and abdomen. In this case, the correct answer should be the correct classification should be head. Okay, because in this input image, there's a head. And now, in order to go more into the detail of this model, I will put you an easier application, which is the detection of a person in an image. No, in this case, the model has to instead of classifying the input image in head, femur, and abdomen, the model has to classify or has to decide or recognize the person in this image, which can be Sarah, Anna, or Salma. Okay. So again, as I said, this model will take the pixels of the image and will process this information in a hierarchical way. This means that the first layers of the model, the first part of the model, will recognize the local features, which can be lines, circles, points in an image, maybe the edges or some shapes in an image. And with these low-level features, the model is able to later detect higher level features such as face features. No, it can detect the eye, the mouth, the nose, and the ear of a person. And in the last layers of the model can detect finally the whole face of the person and make the decision, which in this case is Sarah. Okay, so each of these nodes you see here in this model are convolutions. And the convolution is the following. So it's basically applying a filter to the input image. It's the type of operation that it does is you multiply this number here, 0, in the filter by 9, and then you sum 2 multiplied by 4 plus 1 multiplied by 1, 4 multiplied by 1 plus 1 multiplied by 1, and so on. Here you have the whole operation. And then you get this output, and you put it here in the output array. Then this filter is moved to the right, and then you fill this value here. You move again this filter to the right, and you put it here. Then you go below, and so on. So you go through the whole image, and you process the whole image with this filter. After the convolution, we will get this output array. And then if you apply another convolution, another filter, you will have another output. This is applied sequentially in the model. So just an example of a filter could be this. So in this case, the filters can have different sizes. In this case, it's just 3 by 3, but it can be 4 by 4. This is decided by the one that is developing the algorithm. And in this case, this filter here with this number is called vertical edge detector, because when you apply it to this image using the convolution explained before, the output image would be this one, in which the vertical edges are emphasized. And on the contrary, if you apply this filter, which is called horizontal edge detector, and you apply it to this image, in the final output, you will see that the horizontal edges are emphasized. I just want you to show this example for you to see that when you apply a filter, what you are doing is basically identifying features, different types of features in an image. So each filter is the responsible of identifying the different feature in an image. Okay, so let's go back to the model. As I said, each of these nodes apply a convolution is a filter that detects a specific feature in an image. And this is why we call this model convolutional neural network, because it's a deep learning model that uses convolutions. And it's mostly used, mostly used when you work with images. How does the model learn which are the features that it should learn to make the final classification? So this could be the filter, and in the learning process, you would have to learn which are these numbers, right? These weights. And this is thanks to the loss function or the learning function, and it has this formula. And this could be the prediction of the model, and this could be the real value. And you want this difference to be minimum, because you want the prediction to be equal to the real value. So in some way, you want to minimize this function, and you want to find the most optimal weights, the most optimal features that can minimize this function. So it's an optimization problem, no? You want to optimize, you want to find the best weights that can optimize this function and get to this minimum here. So when after the learning process, the model will be able to detect the most important features in an image to make the final classification. And to do so, you need to see, the model needs to see lots of different examples. This is why we say that deep learning needs a lot of data to learn. Okay, so if we go back to our project, so we know that we want to train a CNN, convolutional neural network, the model I explained before, that could classify the images in these 3 different fetal planes. And we will do it by using a data set acquired in high resource settings, because we will have a lot of data available. We will train it, and then we will test it in another hospital in low resource settings, but using the transfer learning technique that I will explain later, because in this way the model can be adapted to this new data set, to this new context. So the goal of our project was to study the transferability of a fetal plane classification model from high resource imaging settings to low resource imaging settings. So the proposal would be to compare what happens when you train a model in high resource settings and you transfer it in another hospital, but in high resource settings, and compare this situation to when you train a model in high resource settings, but instead you test it or you apply it in low resource settings. Why am I differentiating all the time between high and low resource settings? Basically, because it's the data set you will acquire in these two contexts will be really different. Why? Because in high resource settings, you have advanced equipment, so the quality of the images are quite high. You have a lot of data available, so this is not a limitation. And then the acquisition or the clinical guidelines that were used for the data acquisition are similar. But then when you go to these other contexts, you have less advanced equipment, no? The images are in lower quality. You only have a few images available. This is a limitation in AI. And again, the acquisition protocol is less standardized. So the first step was to collect ultrasound data set in 2 different countries in high resource settings. And this data set had these 5 classes, these 5 categories, which were the femur, the head, and the abdomen, because we want our classifier to classify between these 3 fetal planes. And we also added the thorax fetal plane because we found out that it's also important for the doctor to identify the heart rate of the fetus, of the baby. And finally, a 5th category, which is called other. So when the image does not belong to each of these 4 categories, you would classify it in this 5th class. And we obtained the data sets, one in Denmark and the other one in Spain. The second step was to build the data set in low resource settings, and we obtained these images from 5 different countries in Africa. And again, we had these ultrasound data sets labeled in this with the most common ultrasound fetal planes, the femur, the head, the abdomen, and thorax, and the other category. And just add that in the other category, maybe we could have images that were acquired in a wrong way, or had some noise, maybe some black images, or images with another anatomical region that is not of our interest. And we obtained these data sets in Nigeria, Egypt, Ghana, Uganda, and also in Malawi. Okay, here you have a description of these 7 data sets. And in the first column, you can see the countries. And if we pay attention on the low resource settings data sets, we'll see that these data sets are really heterogeneous, as I said before. For instance, if we look at the second column, we'll see that the type of vendor that was used for the acquisition is different in each hospital, in each country. For instance, in Malawi, they use Mindray vendor. In Egypt, they use Poluson B8. In Uganda, they use Siemens. In Ghana, they use Eden Instruments. And finally, in Nigeria, they use also Poluson, but it was S8, which is in a scanner or an ultrasound machine with lower quality. Then if we look at the frequency range, it's also different during the acquisition, and also the trimester pregnancy. We can find images in 2nd and 3rd trimester, or only in 2nd or only in 3rd trimester. So we can see that the data set is quite heterogeneous and there's a great variability in this case. But then if we go to these data sets that were acquired in high resource settings in Spain and Denmark, we can see that the vendors were exactly the same, the frequency range as well, and also the trimester pregnancy. So when you want to apply artificial intelligence in low resource settings, you can see that it's a bit more challenging because the data set has a higher variability. Here you also have a figure for you to see different examples. So images that were acquired in the abdomen, images of the brain or the head, the femur, and also the thorax. The first column is from the Spanish data set, and we have the Danish data sets. We can see that they are quite similar, but then, for instance, if we go to Malawi, the data set is more darker, and for instance, here the heart, the edges of the heart cannot be seen as well as here, for instance. Then in Egypt, for instance, the images are brighter. We have Uganda, Ghana, you can see that the images are a bit darker, for instance, and finally Algeria, which you can see that the images have a lot of noise, so they are in lower quality. So with this figure, I just wanted to show you that there is a huge variability in this data set. Okay, so the first experiment we did with this data set was, as I said, train a model in high resource settings and then test it in a new center in low and high or high resource imaging settings. So the idea would be this one. We have a data set in high resource settings and we use it for the training. In this case, we had 2,000 patients from Spain. We trained the classifier, the convolutional neural network, to classify between these 5 categories. And later we tested in Denmark in this data set in 1,000 patients in high resource settings. And then we also tested in a data set in low resource settings that was acquired in each of the African centers with 13 patients. The metric we used to evaluate this model was called the average recall. And if you don't know what is the recall, I will now explain it to you. So first, I will explain what it is, the confusion matrix. The confusion matrix is used when you want to evaluate any type of machine learning technique. And you can build a confusion matrix for each class, for each category in your data set. For instance, in our case, we would have 5 different confusion matrices because we have the one for the head, the femur, the thorax, the abdomen, and the other categories we can see here. And I will explain you what it is, the confusion matrix, but for the head. Okay, so here on the left, we have the prediction of the model. And if the model sees an image and says that this is the head, the answer is positive. And if not, the answer is negative. If the answer of the model is positive and the actual value should be positive, then this is a true positive. But if it should be negative because the image is not a head, maybe it's a femur, for instance, then it's a false positive. And the other way around, no? If the model says or gives a negative answer and it should be positive, this is a false negative. And if the answer of the model, the prediction of the model is negative, and it should be actually negative, then this is a true negative. So when we train a machine learning model, we want the true positive and the true negatives to be really high because this means that the model is doing good predictions. So in our case, we use, as I said, the recall metric, which follows or has this formula, is the true positives divided by the true positives plus the false negatives. And we use this metric because we wanted to penalize the false negatives. We observed that when the model was a bit confused, the model was always classifying the image in the other category, in the other class. So we had a lot of false negatives in the other class. And with this metric, we are able to penalize these false negatives in the other class. This is why we use this metric. And the average recall should be the recall of the head, the recall of the femur, the recall of the thorax, plus the one of the abdomen divided by 4. Okay, so the results we obtained were these ones. So when we trained the model in Spain and we tested in Denmark, the average recall in percentage was really high, 90%. The results were really good. But then when we test this model in Malawi, Egypt, Uganda, Ghana, and Algeria, we found out that the results were worse. The minimum value was 41% and the maximum was 74%. So we had to improve this. Okay, and here just to visualize the results. So we trained the model in a convolutional neural network. And when we tested in high resource settings, the results were good. But then when we tested it in low resource settings, the results were bad. What we did to improve this was realign the model, the convolutional neural network trained in Spain, and we realigned this model to this new center in Africa. And how did we do it? We used transfer learning, as I said before, to adapt this model to this new center. And then we kept 13 patients for the testing phase to check whether the transfer learning was helping or not. Okay, so for those who do not know what is transfer learning, now I will explain it to you quickly. As you know, a deep learning model, what it does is it takes these pixels from the input image and processes this information from the pixels to make the final classification, no? Which in this case is classifying the image into these 5 categories that we have here on the right. In this case, the correct answer should be head. And as I said, the model processes this information in a hierarchical way. So, well, in this case, the model was trained using these 2,000 patients from Spain, and it processes these images, no, in a hierarchical way. So first, it detects the low-level features, and finally, the high-level features. The low-level features are general features such as I said, no, lines, points, shapes, different shapes, circles of an image. And these general features are used in lots of different types of applications. For instance, if instead of recognizing a head or a femur in an image, you want to recognize a flower or a car, the model will learn these features for sure, because the model will need them for the final classification. But when you go deep into the model, into the last layers, the model will learn features that are specific to the training data set. So the idea of transfer learning is just retrain the last layers of the model, which are more specific and overfit, no, with the training data set. Fine-tuning, it's the same as saying retraining. It's basically the technical word that we use. And the idea was to retrain these last layers of the model using these 12 patients from each African hospital. So the fine-tuning process is really time efficient because you don't need to retrain the whole model. You just need to retrain the last layers of the model, and you keep the reliability of the model because you keep most of the layers, most of the filters that have been trained with 2,000 patients. So with lots of different examples and samples. So this part of the model, it's really robust. Okay, so as I said, no, the idea is to fine-tune the last layers of the convolutional neural network with these 12 patients, and then test it. These were the results we got. So as I said, we didn't apply transfer learning to the Danish data set because we already obtained really good results. But I just applied transfer learning to these data sets here in Africa. And after transfer learning, we can actually see that there was a big improvement. For instance, in the first case, we went from 62 to 88%. In Egypt, we went from 69 to 85. We reached 100% average recall in Uganda, and we obtained 92 in Ghana and also Nigeria. So we were really happy with these results because by using transfer learning, which is really fast and really easy to do, we obtained really nice results, and just with that 12 patients. Exactly. But we were curious about it, and we wanted to check how many patients we need from the African center to reach the maximum accuracy when we apply fine-tuning. We used 12, but maybe we thought that with less patients would be enough. So these were the results we obtained. Here we have 5 different plots for each African center, and we plot the average recall in percentage depending on the amount of patients that we used from 0 to 12. And what we observed is that at some point the performance increases when the number of patients are increased as well. But at some point it stabilizes, no, more or less at 6, 8. You get the maximum performance, 6, 8 patients, around 90%. So with 6, 8 patients, you get a really nice accuracy, just applying transfer learning. Okay, so these are really good news because it means that with just a few patients, with just a few images, you are able to adapt a model to a new center using transfer learning in this case. So the takeaway messages of this work would be, First, we built an inclusive deep learning solution that was adapted to low resource settings by using transfer learning, or what is the same, fine-tuning. Transfer learning can optimize the performance of an AI model to a new center using only a few samples. In this case, we use 6-8 patients, and requiring minimal effort, because as I said, transfer learning is really easy and fast to apply. And finally, with this work, we want to encourage the development of generalizable solutions for usability of AI in countries in higher need of clinical support. And here you have a list of different resources I would suggest you to look at if you want to learn more about AI, deep learning, and you want to practice. The first is a YouTube channel from a friend of mine. It's in Spanish, but there are the subtitles in English below. And it's really nice because if you don't understand some concepts in AI, he explains them in just 10-15 minutes. So it's nice to see. And then to learn a bit about deep learning, in the very beginning, I did this MIT course. You will see different deep learning methods applied in different applications, and they do it every year. So I would suggest you to do the last one, sorry, because it's more up to date. And you will learn the theoretical part, but also you will have time to practice. And if you want to know a bit more about convolutional neural networks, which is the type of deep learning model we used in this project, you can also check this 1-hour lecture in YouTube. If you want to practice, you have the Kaggle platform that maybe you know it. It's a platform that in which you can collaborate in some competitions, and you can check others' work or code of other people. And then you also have this link to the MICAI Student Board website. As Karim mentioned before, MICAI is a medical imaging community, and the Student Board organizes some webinars and educational challenges that are quite interesting. And finally, the MICAI community also organizes competitions and have some data sets in medical image applications, so you can also check them. And I would encourage you to participate, and because I'm sure you'll learn a lot. And finally, well, here you can find below my email in case you would like to ask me some questions privately. I can also share with you this presentation, and I will be really happy to help you if you have any doubts. And yeah, finally, I would like to say thank you to all these people that made this work possible. Some people helped on the implementation of the model. Others were the responsible of acquiring the data sets. Others in the coordination. So thank you so much. We were a big team. And thank you everyone for listening to me and paying attention. And now if you have any questions, I will try to answer them. Thank you.